Hi everybody. Let's take a minute and practice a bit with common tangents to circles. We're going to look at some external tangent segments and some internal tangent segments. They just have those names because if they pass the line from center to center or not. We'll work out a few of them together, several of them together, and then I'll give you an assignment sort of like that. We'll get started. Circle A and B. Tx is a common tangent to circle A, which has a radius of 13. Get that information in place. And circle B, which has a radius of 6. The distance from center to center, AB, is 25. Let's show that segment. If it's not showing, we're going to need to show it. There, I got the distance from center to center. I am to build a rectangle. And that's the ticket I know that'll solve this kind of a question, is building that rectangle. To get that rectangle started, let's show the radii to the points of tangency. Show the radius of circle A to point T where it appeared to have been tangent, and the radius of circle B to point X. We expect those to be right angles. We're looking to build a rectangle. I ask you, have we got a rectangle here yet? I say, no, opposite sides of this thing are not congruent. To build that rectangle, we should go from point B to line TA perpendicularly, which would look about like this. With that being a perpendicular, we can assume, we can conclude safely that this is a rectangle. And because opposite sides of a rectangle are congruent, we can find the lengths that we'll need here. Let's see how that goes. Circle A has a radius of 13. This full radius is 13. But circle B has a radius of 6. This distance is 6. Opposite sides of this rectangle are congruent, so this distance must be 6. Since this full radius was 13, and this part was 6, that length has to be 7. I seek the length of Tx. That's what I care about, that segment from T to X. But it is an opposite side of this rectangle, so I can find this length that I'm labeling as Z right here. And I know that Tx will be the same as Z, because they're opposite sides of that rectangle. And I have a right angle here, and I got a right triangle to use the Pythagorean Theorem with, bearing in mind that AB was 25. The things that people do wrong, they screw up the Pythagorean Theorem here. You got to figure out where's the right angle and who's the hypotenuse and set up that Pythagorean theorem. I think I'm just about ready to go. I think it would be 7 squared plus Z squared is equal to 25 squared. You check that, be sure I got the hypotenuse in the right place, opposite that right angle. Yep. I think I've set this up correctly, and you might recognize this Pythagorean triple. And if you don't, it's one you might want to memorize. I'll be using it the rest of the year. 49 plus Z squared is equal to, and 25 squared is 625. Let's subtract 49 from both sides, and I'll get Z squared equal to 576. We've got to take the square root of both sides of that one. And the square root of Z squared is just going to be Z. What about the square root of 576? Yeah, it's 24, huh? That Pythagorean triple, that's a 7, 24, 25. And it's worth knowing. So this segment from across there, this edge of that rectangle is 24. So what would be the length of Tx? Yeah, it's got to be the same. Opposite sides of a rectangle are congruent. Let's play some more. Now, switching gears a little bit, this is a different kind of a question. Here we had an external tangent segment, which does not cross the line from center to center. Here we have an internal tangent segment, which does cross the segment from center to center. I'm going to need that segment from center to center. I might as well show it now. In fact, I'm going to build some similar triangles here. I understand that the radius of this one is given. The radius of circle A is 8. And the radius of circle B is 6. I'm going to build similar triangles here and work with the ratio to get the length of segment TX. That's what I care about. Show those radii to the points of tangency. Notice those right angles at those points of tangency. Let's call this intersection place Z, just getting used to that, and recognize that those vertical angles would be congruent. So I do have similar triangles here. A couple angles on this triangle matching a couple angles on that one. Let's make a statement about it. Triangle. I'm going to call mine ATZ. Is similar to the angle at A matches the angle at B, and the angle at T matches the angle at X. So that'd be BXZ. And the reason I want to focus on these similar triangles is I'm going to have to get a ratio between those two. That'll be pretty smooth. The radius of this one was 8, and the radius of this circle was 6. And aren't those opposite congruent angles? So those sides are corresponding parts. So the ratio between those two triangles is 8 to 6. You ought to reduce every ratio you get, every chance you get, and that's a ratio of 4 to 3. All the sides in this triangle compared to all the sides in that triangle, all the corresponding sides will be in a ratio of 4 to 3. But notice this, AB has length 21. This length and this length add up to 21. And those are also corresponding parts of these similar triangles. The hypotenuse of this one corresponds to the hypotenuse of that one. Those segments ought to be in the ratio of 4 to 3. And because AB is equal to 21, and is broken into segments that are in a ratio of 4 to 3, let's figure out the lengths of those two smaller parts of segment AB. If they are in a ratio of 4 to 3, we can call them 4x and 3x, and they add up to 21. We see 7x equals 21, which gives me that x is equal to 3. Now, I don't know that any segment is equal to 3, but I have a segment that is equal to 4 times 3, and a segment that is equal to 3 times 3. That 4 times 3 would have been 12. That's the larger of the two. That would have been made this length be 12. And the hypotenuse of the other one must have been 3 times 3, therefore 9. And now I've got a couple of sides on a right triangle and a couple other sides on that right triangle. I think it's smartest to work on the smaller one first. It has smaller numbers. And so I'm going to jump in here and hit with the Pythagorean Theorem. I'm going to find that segment ZX. ZX squared plus 6 squared. Being careful who's the hypotenuse here. And the hypotenuse is that 9 opposite this right angle is equal to 9 squared. Let's play through that one. ZX squared plus 36 is equal to 81. We best subtract 36 from both sides, which would leave ZX squared is equal to 45. Taking a square root of both sides. Square root of ZX squared is just going to be ZX. What about the square root of 45? You know any perfect squares going to 45? Yeah, it is 9 times 5. I know the square root of 9. We'll call that 3 times the square root of 5. Now, I got this little length, ZX. That's not all I wanted. I want more than that, but I think that's 3 root 5. I understand that these two triangles are supposed to be similar in the ratio of 4 to 3. If this one is 3 root 5, don't you expect this one to be 4 root 5? Let's verify it. I might want to do that on another piece of paper. I don't want to crowd this up too much, so let me just play that through right here. Going to hit this with the Pythagorean Theorem in the other triangle. 8 squared plus TZ squared equals 12 squared. 8 squared is 64 plus TZ squared equals 144. Subtracting 64 from both sides, we'll find that TZ squared is equal to 80. Take the square root of both sides, and TZ itself must be, well, what do you know about the square root of 80? Yeah, it's 16 times 5, and that makes it be 4 times the square root of 5. Probably what you were thinking already. I come back here and reply that this length is 4 times the square root of 5. Makes sense because this one was 3 times the square root of 5, and these triangles are in a ratio of 4 to 3, huh? So, I better finish up with how long is tx. That's what I'm supposed to come up with here. If this length is 4 root 5 and this length is 3 root 5, yeah, I can add those up, can't I? They have the same radical. I got 7 root 5, don't I? 7 times the square root of 5, whatever that amount is. And that's how long our segment tx would have been. Let's practice some more. Here we get that common external tangent. An external tangent does not cross the line, the segment from center to center. We're going to need that segment from center to center. We're going to build a rectangle here, aren't we? I see that this circle has a radius of 14. And this one has a radius of 8. And I know the typical way to find the length of a common external tangent segment is to build that rectangle. We'll show the radii to the points of tangency. Admire those right angles. We got a couple of parallel lines there. A couple of right angles, but that's not a rectangle. That's a trapezoid right there. We need to show that line from B to segment TA that is perpendicular. And then I've got the rectangle that I need to work with. I should bear in mind that this radius was 8. Opposite sides of that rectangle are congruent, so that segment has to be 8. This full length is 14. This radius is 14. This part must have been 6. I got 6 and 8 adding up to that 14, and that makes sense to me. And the distance from center to center, AB, is 26. I'm going to find this length Z again. That lives in this right triangle with a right angle here. When I know that distance Z, I can conclude safely that the opposite side of that rectangle is the same amount. And that's what I care about is segment TX. So let's get Z. Hey, mister, where's the right angle in this guy? There it is, connected to that rectangle. And the opposite that right angle is our hypotenuse. So let's be absolutely certain that 26 is the hypotenuse here. We'll go with 6 squared plus Z squared is equal to 26 squared. Let's burn that down with the Pythagorean Theorem. I got this part 36 plus Z squared equals, and 26 squared is 676. We got to subtract 36 from both sides. Z squared will equal, and 676 minus 36, I think that's about 640. I'll take the square root of both sides. You'll be thinking about reducing that radical. Square root of Z squared is just going to be Z. What do you know about the square root of 640 anyway? Well, it is 64 times 10, isn't it? So that segment Z is, as we reduce this radical, I do know the square root of 64, it becomes 8. I do not know the square root of 10, it stays within the radical, so 8 root 10. And that's our segment Z, and therefore it is the segment TX as well. 8 times the square root of 10. That's a nice little workout. Let's go one more of these. Segment TX here does cross the line from center to center. That makes it be an internal tangent segment. And we're going to work with some similar triangles to find the length of TX here. Circle A has a radius of 6. Circle B has a radius of 4. Show those radii to the points of tangency. Let's get those similar triangles showing. Get the right angles in place. We might want to call that point Z just so we can talk about it. The vertical angles at Z are congruent, verifying that we do have similar triangles here. I'll make the statement, triangle. If I call mine ATZ, is similar, worth writing this down, to triangle. The angle at A matches the angle at B, BXZ. And let's get that ratio. Yeah, the radius of this one was 6, and the radius of that one is 4. And those are corresponding parts, so that ratio's got to be 6 to 4. Reduce every ratio that you could. That's a ratio of 3 to 2. Now, let's put to work the idea that the center to center distance, A to B, is 20. All the way across here is 20. But I got to get those two parts of that segment AB. I know they're in a ratio of 3 to 2, and I know they add up to 20. And the cheapest way I know to go about that is to say 3x plus 2x. This represents anything in a ratio of 3 to 2. But these things that are in a ratio of 3 to 2 have to add up to 20. That gives us 5x equal to 20. Dividing both sides by 5, I'm pretty sure that x had to be 4. No segment is of length 4, but I got a segment that's 3 times 4, that'll be 12. And one of them that's 2 times 4, that one would have been 8. Bigger triangle gets the 12, the smaller triangle gets the 8. Now, we got to go figure out about tx. I think it's smartest to figure out about the smaller triangle first. Then we can generalize to the larger one because they're similar. Let's hit it with the Pythagorean Theorem and get that length for zx. I think this might be a special triangle you might recognize. I see that this side is 1/2 the length of the hypotenuse. That tells me things about it. If I was working with that smaller triangle, 4 squared plus zx squared is going to equal the hypotenuse 8 squared. So I've got 16 plus zx squared is equal to 64. I had to subtract 16 from both sides. That would leave me with zx squared is equal to, and 64 minus 16 is 48. Let's take the square root of both sides of that and get zx itself. Hey, what do you know about that 48, huh? 16 times 3, you figure? So that'd be 4 root 3. Now, is that a triangle that you recognize if this length is 4 root 3? Yeah, I think that's a 30, 60, 90 triangle. I see that the short side is 1/2 the hypotenuse, and the short side times the square root of 3 gives me the longer leg. So that is a 30, 60, 90 triangle, and this one must be similar to it. I'm going to act like I didn't notice that. I'm going to hit it with the Pythagorean Theorem and find this length tz. 6 squared plus tz squared is equal to 12 squared. And this short side is 1/2 the hypotenuse, isn't it? I got 36 plus tz squared is equal to 144. Got to subtract 36 from both sides. I got tz squared is equal to 108. And we'll smash that. Take the square root of both sides, and tz. What do you know about the square root of 108, mister? It's 36 times 3. This makes me think that would be 6 times the square root of 3. Meanwhile, back at the ranch, if this length were in fact 6 times the square root of 3, does that go along with this being a 30, 60, 90 triangle? Short side times the square root of 3 gives me the longer leg. Yeah, that's a couple of 30, 60, 90 triangles there, but what we care about was the length of tx. How long do you think tx is? Well, this part was 6 root 3, and this part is 4 root 3. Shouldn't we call that 10 times the square root of 3? Now, I've got a collection of